Welcome to Computer Programming, Part 1, Setup. So this slideshow is meant to accompany the lecture material and to give you some more labs into why computer programming is important and some different things you can do. So for this course we're going to be using Texas Instruments MS430 Launchpad, which is a very nice programming environment and a very nice way to do and start to learn embedded programming, which is a very fun way of doing programming. So we'll start there. So first, why is learning computer programming important? So computer programming gives us the ability to customize things. Everything now is running on some kind of computer program. Digital electronics have computer programs. We have computer programs running the internet. This website is run by a computer program. The software used to record these PowerPoints is another computer program. Computer programs are everywhere and in our current environment. So the ability to customize things like that and to change them is a very powerful addition of tools to the engineering toolkit. The next thing that we can do is we can add additional features to software and increasingly electronics. So when you get to a certain point in programming, you can find and open other software and add to it. You have to be careful that when you do this, though, that you don't void any agreements or any signed papers. So another thing that you can do is you can also save time when you're performing repetitive tasks. So for instance, if you're making a part in SolidWorks and you have to keep clicking each individual little hole out of this part, and there's 9,000 holes, this could take too long to do. However, programming allows you to automate that procedure so that you can select all 9,000 and click, 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 click automatically and save yourself carpal tunnel syndrome. That's a good thing. So another thing that we have is it can also, programming conceptually teaches someone how to break complex problems down into smaller conquerable chunks. So this is a very important theoretical concept, that whole software systems like Windows 7 or Mac OS or any of these giant software systems are actually created from very, very small sized chunks that gradually grow together. So in this regard, we can kind of think of programming kind of like how our body works in the regard of DNA and small pieces of information. So in our body, we have many, many small pieces of information in DNA. We have 4 letters essentially that create our genetic code, and these are arranged in different patterns, and as we evolve, these patterns started to become more and more complex, and this complexity built off of each other, and then those complex pieces became more, and complexity increases exponentially. So therefore the same mindset can be used with programming, where we have very small little pieces of program that we can start to put together into very complex things. Another thing that we have with programming that's conceptually important is the linear step-by-step thinking and debugging, which is useful in many other applications, especially in engineering, where you have a problem where you don't know exactly where your problem is coming from, but you know that you have it, and then you can start testing it and debugging. Is the problem caused by a mechanical failure? Is it an electrical failure? If it's an electrical failure, is it digital or is it an analog component? If it's a digital component, is it part of your code or somebody else's code? And so you can start to break down these very complex problems and debug them piece by piece, which is very important. So, why is computer programming my favorite class? So I've had the opportunity to take a lot of engineering classes, both in architectural engineering undergrad and also in biomedical engineering for graduate school. And I think programming is my favorite of the engineering classes. So in programming, everyone starts on the same page. So most likely none of you have had extensive coding experience before. Maybe you've had a little bit and dabbled in it a bit, but essentially programming has not really propagated down to the high school system yet, and so therefore everyone in this class is starting on the same page pretty much on the amount of coding you've done before. So coding is also not dependent on calculus or other mathematics. This, if calculus or mathematics are not your strong suit, this gives you another opportunity to solve those types of problems in new creative ways. So programming also can open up a new level of mathematics that can't really be done by hand. So for instance, there are finite element analysis, which is a giant simulation of the mechanics of some part. So maybe you make a tire or an axle, and you make them in SolidWorks, and you want to see if these tires and axles can hold up to a certain amount of stresses and loads. So what you do is you create this part, and then you have very, very complex analysis that would take many, many months, if not years, to do by hand, but a computer can do it immediately in a couple of minutes. Therefore, these incredible equations can be harnessed at a much simpler level, and coding and computer programming can open up more mathematics and more tools to you. So programming also depends on logical systematic thinking. It's another straightforward kind of thought, but if you think about it, logic behind programming, and programming teaches logic, and logic teaches programming. So that's something that we'll be working on this semester, is to look into how you can change, how you can better your logic, actually. So another reason I really like programming is that it's less based on natural skill and more based on the time committed. So to many people, logical thinking is not a natural activity. We're not naturally, I would argue, logical thinkers. However, it's something that you can work on and you can learn. It's also something that the more time you spend on it, you significantly get better. So coding really rewards, and computer programming really rewards the people who are doing it constantly. So I even notice now when I go for a couple weeks without coding, it becomes a little bit slower to go back into it and to start to do new projects. Keeping that fresh and keeping algorithms fresh that you can use, and setups fresh, and your software environment fresh, allows you to become a much more efficient and much faster coder. So essentially, you want to be able to get better at this course, you want to be able to do much time into working on the materials, more than is required for class. And with that, different doors can open up to you, which is why I left the last section here. I like it because of jobs. So I found, especially in Germany, there's a lot of positions for young graduate engineers to do coding for principal investigators or other professors who have a really nice idea, who have a project already set up, who have data collected from it, but really they need somebody to be able to take this giant swath of data and analyze it down into something much smaller, something more manageable, and then to do processing with it for statistical processing or different types of analysis. So there are some entry-level graduate jobs there that require heavily programming, and if you have a good basis in it and you feel secure in it, these could be a very nice way of getting into grad school, master's and PhD and whatnot, and getting that paid for you. So this is another nice thing to be thinking about when you come to computer programming and why it's important. So, examples of computer programming. The first set of examples we have is the internet, which is probably the most obvious. Google, Facebook, Twitter, LinkedIn, YouTube, Pandora, personal websites like this, all of these are running a type of programming. So they can change. Generally, websites are displayed by kind of almost a scripting language. It's not really a programming language, I would argue. It's HTML, and HTML allows you to display and see whatever you're seeing. So this website is coded in HTML. It's not very reactive, it's more of a kind of one way from a server to you, although things are changing with newer versions. But with that being said, there's PHP, which is an interactive and full programming language, Python, which you can use as a backend. So there's a couple of nice programs like Django, which allow you to write code. So for instance, let's just look at Google. Google runs a variety of different types of computer programming. It runs as far as I can understand and remember, it runs some C in the background. We have Python. Python is a fast language to code in. That's one of my favorites, actually, if you're trying to prototype something quickly. The problem with the speed of writing code, because you can write a whole web server in a couple of lines of code, which is phenomenal, using something like CherryPy. But the problem with that is that it's not very efficiently written code. It's not compiled, it's interpreted. And we'll get into more of these terms later. But something like C is a compiled code and runs a lot faster on the computer. So something like for image processing or whatnot, we'll go into C. But anyway, the internet is written very heavily by different types of computer code. This website is also, and I can show you how to do websites at some point in the future if you'd like to learn how to do that kind of thing. Another example of programming is for productivity. So a lot of commonly used programs right now in engineering have scripting back engines, and these scripting contain full languages like Visual Basic or Python or one of the other different languages to allow you to make high customization and remove repetitive tasks. So over here on the right we have something from Dr. Pasteur's class in which you're looking at fiber and composite layer properties. And so creating back-end programs allow you to calculate out very quickly different procedures that might take you a lot longer to do by hand. Essentially, it saves time. You can automate these procedures to be able to be completely automated so that you click a button and everything follows every time. SolidWorks is another great one, which I already explained. You can use the SolidWorks API in order to automate the construction of different parts and build them automatically, or start to do scripting like in Rhino. So in the School of Architecture, they use Rhinoceros 3D and a couple add-ins like parametric modeling called Grasshopper, or another Python script to be able to start to build more complex buildings than you could draw by hand. So things that build off of the environment, things that respond to the environment. For instance, having the building become optimally shaped to avoid wind, or having a building to be structurally sufficient and automatically calculate the structural poles. These are all things that can be scripted into other existing programs. Again, ONSYS or ANSYS, depending on who you're talking to, has some different scripting engines in the back end too, and you can use those to quickly speed up the process of finite element analysis. And so finally out here, you also have machine output cleanup. So if you're using a piece of testing equipment, such as the Instron down at the Philadelphia University Research Center in Manayunk, you can take the data off of that, which is a very large data file, and you can extract only the pieces that you want to see, and then have those extracted pieces put into a file that you can very quickly graph and plot in Excel. And this saves many, many hours of hand-clicking individual data cells, copy and pasting into a new file, and essentially saves you time. Becomes a good level of efficiency. Another example of computer programming is the writing of custom software. So here in custom software we have web scrapers. Web scrapers are interesting programs that will look through the web and kind of automatically just kind of crawl around the web and start to pull data off different websites. So for instance, you can crawl around on SEPTA's website and see when the next train comes to East Falls. Or you can crawl around on the weather site and you can pull the weather data. And you can pull all of this and display it in one page. So maybe you make a web crawler like Homepage that pulls all of the interesting data to you off of the rest of the websites and shows you at one spot everything that you'd want to see. That's something interesting. Custom software also exists for cell phones and cell phone apps. It's a very growing market right now, and writing code for Android and iOS, very big, prolific. We might get into a project or two like that in this course. We have data collection from different sensors, from thermocouples, whatnot. We have writing custom software for file transfers or FTP servers. You can write your own way of sending information from one place to another, or you can even write your own encryption for that information so that nobody can decrypt it as it goes. We also have remote computer control. If you want to set up your computer to control other computers around you, you can write your own scripts and whatnot to do that. And so for instance, right now I'm using this laptop which remotely connects to 8 other computers around campus, and that way it distributes the load on my laptop and I can get more things done without ever waiting for my laptop to catch up. So on the right here we have a filament winding machine I programmed up from scratch. This would have been about 2 years ago, and this allows you to make composite forms, composite tubes on that mandrel. And so this is another application of programming. This was written in a customized programming language, which is customized for that chip you can see there on the right sitting on top of the power supply. But essentially it's a computer-controlled filament winder, kind of CNC controlled. So you can start working with other things like that as well. Another example of programming, we have digital electronics. So digital electronics are one of the primary things we're going to be focusing on in this course and in electrical engineering. And these consist of things like microcontrollers, which is the MS430 that we're going to use. Taking sensor readings, you can build 3D scanners. So on the right is a 3D scanned image I made in college on a 3D scanner built with a broken projector. And you can do a lot of different types of programming with that kind of thing, extraction of data points, using cameras, displaying outputs, and then interfacing this to the internet, interfacing all of these so that you can control them. So this is all kind of the swarm of digital electronics. And then finally, probably one of my favorite, we have mechatronics. And mechatronics is the combination of mechanical and electrical systems. You can do things and program things like robots here. We can program CNC equipment, custom test rigs if you want to test something or the loading conditions on something, or have something do cyclic loading again and again and again. Well, you kind of don't want to sit there and keep using it, so you make some programs to automatically move and test things. So essentially, this is another really fun example of programming where you start to interact with the environment around you. So on the right, you can see a hexapod, which is kind of a small robotic hexapod, small robotic insect that you can build, which has gearing and motors and whatnot, and can crawl around or whatnot. We might get into hexapods in one of the classes this semester. So first thing to start out that's most important, what is a microcontroller? A microcontroller is a chip that allows an interface between the digital world and the physical world. So this chip allows you to talk to things in the real world with a little bit of code. So previous to the advent of digital electronics, we had analog electronics. Analog electronics are very fast-moving. They work on signals and larger mathematical equations generally. Digital electronics work on code. So each one of them generally can do the same kind of goal in the long term. As we get better at digital electronics, actually digital electronics seem to be able to surpass what you can do in analog, and I know there's going to be people that argue with me on that, but so digital electronics consist of a chip. So on the right we have microchips PIC 18F2455, which we have a couple labs for as well. It's a very interesting chip, very powerful chip. On this little tiny black piece with these little pins, you have a full computer which can do processing. It has it can run different commands, and also it has some memory in it to store different parts of those commands. So this microcontroller's pins on the side, those little silvery parts, are the way that that chip interfaces to other digital electronics or to the world in general. So essentially we're going to be focusing on microcontrollers in this lab. So here we have what is an evaluation board. So an evaluation board allows you to evaluate or use a microcontroller without the hassle of setting up the smaller electronics. So if you look at the picture on the right, you can see where that little tiny microcontroller sits in the board, and you can see that there's a lot of other electronics here. So if we go to the other microchip slide we just saw, you would require some of these other peripheral electronics to do it. So essentially, why do we use an evaluation board? It makes developing new ideas faster and more predictable, because now we don't have to worry, does this other resistor not work, or did this capacitor not get put in right, or is our breadboard or something not correctly collected or whatnot. So it reduces the time spent debugging and lets us just jump into better projects faster. So, microcontroller comparison. Right now there's quite a renaissance in the microcontroller world. There are tens, if not hundreds, of different development boards. We have Raspberry Pi, we have the BeagleBone, we have Arduino Duo, we have all the different Arduinos, we have Mint, we have the NetDuino. All of these boards are competing to be the most used board. So generally right now it seems to be that the Arduino Uno has been most successful, also the Raspberry Pi in capturing that market. However, newer chips are coming up with more features that are cheaper, that run faster pretty much every month. So that's something that we try to look at when we're doing this, because these boards become outdated very quickly. So the board we're going to be using for these tutorials are the MS430, specifically the F5529 series Launchpad. This is created by Texas Instruments, and you can see a picture of one shown to the right. And this board has a lot of very interesting features. It has a built-in USB programmer, so we don't need other electronics to program it. We can just plug in a USB cord and plug it into our computer and start talking to it and making it do things. It has a 25 megahertz processor, and this processor is can run different instructions very quickly. We have a 16-channel 12-bit analog to digital converter, which we'll go through again later. We have methods of communicating with other chips, which are the I2C, the SPI, the UART, and we'll go through these again. We have 40 input-output pins, which essentially could be LEDs, they could be push buttons, they could be changeable to different things. This development board is very low power, and the best point about it is it's low cost. So while the features are around the same as the Arduino, as one of the Arduinos, we get about a fourth the cost because the Arduinos are around $30, $40 right now. So this is another good plus feature. So here we have a description of the MS430F5529 board. You can start to go through it and to see what some of the different pieces do on here. The things I would like to note are the microcontroller, which is smack in the center of the bottom half of the board. The top half of the board, where it says Launchpad and it has two little dotted lines to each side of it, the top half is used for programming the bottom half. So the top half allows you to connect it to a USB in your computer, and it also does some of the debugging so that you can see where your errors are happening. This is very useful for us. The bottom half is more the part that we interact with on a normal basis. You have two push buttons on the bottom that you can program to test things, and then you have two surface mount LEDs on the bottom as well that you can see to make sure things are working. You can use these for debugging often. So for the input to the MS430, we have sensors, and sensors can be anything. There's hundreds and hundreds and hundreds of sensors that you can readily plug into your microcontroller. Libraries exist for many of them, and if not, it's not too hard usually to write up a new library to include a new type of sensor. But sensors include light, color, images, temperature, sound, location, GPS, buttons, hundreds of different sensors, and all of these can make the microcontroller perform a new action. So the microcontroller itself does the processing of these signals. So this is where we get into control loops and feedback theory and control engineering, which comes up later on. It's a senior level course. But essentially you can do very simple PID loops and whatnot rather easily using your microcontroller in the MS430, and this allows you to do more automated and more controlled processes. So essentially we can take a sensor, we can listen to it, the microcontroller can determine what equation we're performing on that sensor or what we want to do with it, and then we can send it to an output. And the output can be anything from different types of motors like stepper motors, servo motors, solenoids. You can increase the voltage, you can operate valves which let fluids through, you can heat things, you can change the lighting. All of these are output from the MS430 that you can interface to. So we're going to go through again all of these individual types of outputs in a later video. Right now we're just going to know that they're there. One of the most common outputs though that we use and that we'll use in these tutorials are LEDs. And we use LEDs because they can be cheap substitutes for motors. Instead of a motor turning on and starting to spin very quickly, we can look, is the LED lit? And that way we can see very, very quickly that things are working and that things are getting power and that our code is working. So LEDs are very easily swapped out for motors using transistors and relay circuits and things like that, where they allow you to bump up more power. We use LEDs also because they're a lot faster to program in, to plug into the breadboard and to work, and they don't require these advanced power circuits like I said. So the first thing that we're going to do to get started is to program our MS430 through the USB. So using our computers to write code and send it to the MS430 to do things. So there's two ways of doing this, Code Composer Studio and Energia. So Code Composer Studio has been around for quite a while. It was written by Texas Instruments, and Texas Instruments has has gone through it. They've done a very good job at making it long and working to have a lot of different details in there. And it's an industry standard for coding microchips. So the industry has often used this. It allows for a lot of maximum features, optimizations. Essentially, the problems with it is it's a very long process to learn how to use. It takes quite a while. It takes a lot of effort. Lots of little things change, and also you need to have a very setting computer system for it. So once you set up the computer system, generally you won't play around with it, and you'll just use that as the dedicated programming system. Generally, if you want a professional license for this, it's very expensive. So Energia, on the other hand, is a very small platform that's been open written by developers and hobbyists. It's more bent towards educationally learning about these chips. It runs the some of the features have been removed that you get with the code composer and doesn't run as fast and whatnot. But essentially, it's a good programming environment for starting. It's much quicker to learn, and you don't need configuration files. Oh, and it runs on Macs, which is important. So the next thing we're going to do is to do a download and run Energia and see how we have our setup going and try to make a first little test program. To get our coding working is to download Energia, which is a easy-to-use software programming utility for the MS430 Launchpad. So there are multiple ways to program it. I'd say primarily the industry way is to use the Code Composer Studio by TI, and that has a lot of advanced features that really maximize the use of your chip. It has some optimizations to make sure that you can fit the most and get the most out of the memory in the chip that you have, letting you use some lower level chips. For us though, however, we're looking for something that's a little easier, less learning curve to begin with, and allows us really just to open up and explore the wonderful Launchpad platform. So the first thing we're going to do is search and download Energia. And so here you should find it, energia.new. Good thing about Energia is that it is software independent, so there are many different types, platforms, computer hardwares, and operating systems that are supported with it. So Energia sketches, as it says down here, are based in C and C++, compiled with open source compilers. That means essentially that they've done the hard work for us to make it a very easy to use piece of software. So what we're going to do here is download. We're going to find our version. Currently I'm using a Windows machine, so you find the one that matches your system. I'm going to download it up. And we'll come back when that's done downloading. So the first thing we're going to do to use Energia on Windows is to install the drivers, and you'll have to do this as well for Mac and Linux people. So what we're going to do is go down, we're going to find the 5529 driver, and we're going to download that. That's the Launchpad that we're currently using. This open folder. Now we're going to extract all. Extract that to that folder. Yep. And now we're going to run the 64-bit because we're running a 64. So after Energia is downloaded, we want to find the compressed folder, and this is again for the Windows operating system. If you have Mac or Linux, you're going to follow a slightly different procedure. But we're going to right-click on the zipped folder, and this will allow us to decompress the contents. So we're going to decompress it to the same folder, extract. Here we could also decompress this to a flash drive or whatnot. Although it doesn't run as smoothly on the flash drive, it seems to be okay. I would recommend putting it on your hard drive or keeping the zipped file on your hard drive, and that way you can uninstall, you can reinstall and run it on different computers, including school computers. So while this takes a while, we're going to pause while this is unzipping. So now that we've downloaded and extracted Energia, I moved the entire folder to a location on my C drive. And so I initially tried to click run, and I get a problem you forget your sketchpad. Energia cannot run because it could not create a folder to store your sketchpad. And this error is because the default location on my laptop, it's a FiddlyU laptop, and therefore is Juno. So once you connect through a VPN, and if you don't know how to connect through a VPN, see that tutorial as well. But once you connect to your VPN, you're connected to the drive, and then once we run it, we're going to try again, it should run totally fine. So now it's booting up. Here. So here is our Energia sketch. So what this does is, this is essentially how you program your chip. So what we're going to look at now is the part portions of it. So right now up here we have our void setup, and so anything that we put inside here is how we set up the chip. How we set up if we are going to have the pins be outputs so we can turn LEDs on, or if we're going to have the pins be inputs so we can listen to push buttons or other analog sensors. It's going to set if we're going to have some kind of communication protocol, USB or UART or I2C or SPI. All of these we'll go through later. They're just ways of having the chip talk to your computer, or the chip talk to other chips, or the chip talk to other digital electronics. And so you set all that kind of thing up here in the setup. Down here inside the void we put our main code. So the void is in a loop, and therefore it runs continuously. The setup runs one time at the beginning, it sets the chip up, and then essentially it's done. So the loop is where we have things that run repetitively, and this is kind of where the power of microprocessors and microcontrollers is. You can set a task up to go for as long as you'd like, and there's not a problem. It just keeps running and running and running. So generally in computer programming we try not to have tasks run continuously, because if we have loops that run continuously, generally that sucks up a lot of the processing power of that computer, and often Windows will detect that huge amount of power being used, and therefore will try to stop it, or you'll get something that says not responding or whatnot. So even sometimes when I'm running like Python programs, I'll get a Windows notification that says Python is not responding, and it is responding. It's working in the background. It's just working 100% and using a huge amount of your processor, which Windows thinks is incorrect. So with microchips, so that's how you do it. They run continuously, and you use all the processor that you can. There's no real penalty for that in the kind of code that we're going to be doing. So anyway, other things about this window. This is your Energia window. Like I said, this is how you communicate to the microchip. So this little check mark here, verify, and that's a way of checking that your code is working. When you click that check mark down here, you're going to have it compile. Now, what does compiling mean? Compiling means I'm going to take all of the words and English that is there and make it into computer language that the computer can use. So right here, if you look down, you'll see a cpp.hex. Hex files are generally the file that we upload to the microchip. And we can go more into that later. Right now, you don't really need that to get started, but essentially what I want you to see here, the important part is that we're compiling. We're taking this written code and turning it into a hex pattern, or essentially, if you want to go a step further, to a binary pattern that we can upload directly to the chip. And that runs our individual code. So that's the first part. So the first thing we do whenever we compile something, or whenever we make a new project, is we compile it, and that checks to make sure that we didn't make any errors in typing, that we didn't type something incorrectly, or that we closed all the brackets. This has a nice feature that if you click on a bracket, it shows you where the other closing one is, which is very nice. Same with braces. However, yeah, that's that. So the next step that we have, once we compile it, we'll get a nice thing that says down here that it's done compiling. There's no errors, otherwise it flashes with errors, then you have to go to that individual line of code and fix it. So after we're done compiling, we can upload and click on that, and that sends it directly to our chip. And so that's how we can push the working code to the chip. Generally, we always do the verify first and then the compile. The compile first and then the upload. And this is more procedural. This also gets rid of debugging errors. So always do that. If you just click the upload, it will compile and upload. However, you won't. It's a little better practice to click the verify first. So the new is for new sketches. We have open for other sketches, and we have save, of course, so that sketches are the program that we have here, and this one automatically names sketch and the date that you're recording it. If we go over here, you can do the same thing, new, open, sketchbook, and whatnot. So the sketchbook is where you store all your sketches. As we're brand new, we don't have anything in there, so it won't open. Example code is very critical in this. So the example code is something I rely on heavily, and I think you will as well. The example code goes through many different individual codes that are automatically installed when you download Energia, and these things can really help you debug problems and build more complex things fast. So in the example code, the first thing we have is analog read serial. We have something to make the light blink, which we'll go to later. We can read the serial. We can read an analog voltage. This is used for like temperature sensors and some other analog sensors. We have a bunch of digital things like blinking. We can make tones and sounds. In the analog, we have a couple other analog functions. Communication, we can start loading MIDI, like a MIDI keyboard. We have some other ones down here that we'll go through later. Control, we have arrays, we have switch cases. I believe somewhere in here we have interrupts as well. Strings are kind of strings are words, like verbal words. So the variable cat or dog is a string, and so this allows us to do some things with them, and we'll go into that later. Sensors, they have a couple predefined and pre-made sensor types here that help out a lot, and then display, and then some other things as well that are common. So we'll go through more of these later as we get going, and that'll be how we do it. So in the edit, nothing special there, just normal editing menu. Verify and compile, which we did. Copy hex file as path. So this allows you to copy that little hex file that it produces down here and save it, and that is a very co-composer studio way of doing it. You can export and upload the direct hex file, and that way you know your file kind of stays the same and it's the same version, nothing really changes, because it's more difficult to change a hex file. It's easier to change it by clicking another letter or something incorrect in this document. So we have sketch folder, import library. We can use these later to import other people's libraries. So libraries are bits of code that somebody else have written, and they work really, really well to do more complex things. And instead of rewriting the entire thing from scratch, you want to be able to import as much from somebody else as possible and try to make it work that way. Tools over here, format, we don't really use that. Serial monitor is very important. We're going to go into that in a minute. Board, we're going to pick whichever board we have. So this is the first thing that's important to do. So looking down, we have our MS430F5529. That's the board we're going to use for these demos. So we're going to select that one first. And now we're going to go to serial port. It gives us two options of serial port, and we're not exactly sure which serial port this is right now. So what do we do when we're not sure? We go to Command Control Panel, and now we can also go to Device Manager, and Device Manager will start to be able to show us exactly which devices exist on the computer. So this is an important step if you're ever having problems with finding the programmer, with finding the chip. So if it says it cannot be found, or if you're having some other startup problems in general. So we're going to go here, we're going to click real fast, we're going to generally sometimes we click refresh or whatnot. I think here it's already loaded up. If we scroll down, so we have two things, because we've just plugged in the program, the microchip, and the two things here are a UART on a COM8 and an MSP debug interface on COM7. And again, so we can see that it's connected right, and we'll go through what more of these mean later. So to go back to this initial tutorial, we change the serial port for whichever one it is, depending on what we're trying to do. Also, we have a help. The Energia.new and the support forums on 43.0 are really good, and I highly recommend going through there if you have any questions and setting up an account so you can ask, and also so you can give back a bit. Now the final thing about this that's really important is the serial monitor, and we're going to click it now. We can't run it right now because it's not set to the right COM port, but the serial monitor is a way for us to get direct feedback from the microchip. So essentially it's the way of the microchip talking back to the computer. Now this is important because right now everything we've done is from the computer to the microchip and microcontroller. This is very good. The serial monitor is very good for getting debugging info back. So if something is going wrong, you can use that to diagnose exactly where in your program the problem is. Furthermore, the serial monitor can be used to pull data in between programs. So you can also cleverly use the serial monitor to save data from your microchip into an Excel file so that you can process it later. So that's another very useful tool. But for now, I think this is where we'll stop, and we'll pick it up later with setting up some code and uploading things to the microcontroller. So once we've plugged in our MS430 microcontroller, then we're going to see a removable disk come up. This is the first time that we plug it in after the unboxing. Once you change the programs around on side of it, this won't happen. But anyway, this removable disk comes up, and then inside you'll see a couple different, 4 different folder files: button 1, button 2, MSP Launchpad, and the README. Essentially, the README is saying that if you press the button 1 on the Launchpad, you're going to get the text in button 1 to come up. In a document, it doesn't matter if it's Word or Notepad or whatever, if you press button 2, you're going to get a little ASCII art of a little spaceship launching off. And so what we're going to do right now is just to prove that, we're going to create a new folder. We're going to create a new text document. Doesn't matter if we name it anything. We're only going to keep it for a moment. We're going to click inside that text document, and then we're going to click on the very first push button at the very bottom left of the board, on the exact opposite side of the USB cord. So if we click it once, it types out hello world into our document. We can click it a couple of times and you'll get hello world, hello, hello, hello. Every time you click it, it'll print it again. So this is just demonstrating the properties that you can have kind of a USB device with this. So this doesn't have to be one way. So in the future, this could be expanded to make your own keyboard or your own mouse or some other type of data input towards your computer. So now that we have Energia running, we're going to check to make sure that we erase that lovely little Hello World program that they automatically installed on it, which was good to show how the push buttons work and that you can type into a text document. However, ultimately, we would like to be able to put our own codes on there. So the first thing that we're going to have to do is go to Device Manager, and in Device Manager, we can figure out exactly which device we have. So if I open up Device Manager here, you see that we have our MSP debug interface and our MSP application on the UART. So we actually want to make sure that we are using the one, which one of these that we're using is the correct one. So one of these is that little hard drive with the push button, the Hello World, and the little rocket on it, and the other one is actually the platform to program this and reprogram this entire chip. So if we go to Device Manager again, you're going to see down here that we have, if we do a quick little scan for hardware changes, I think I changed, so we're going to want to program to the UART one. So if we close the Device Manager afterwards, we're going to go to Tools, we're going to go to Board, make sure that the MS430F5529 is selected, and then go to Serial Port, and then we're going to select the one that has the MSP application UART, which in my case is the COM8. So once we click that, we're going to select it, And now we're going to click Update Programmer. So this updates the firmware on the chip to make sure that it has all the new things. So we currently have all of the firmware updated. Once that's done, you're going to be able to do make sure that's still selected. You've already updated. Now we're going to compile this brief little sketch. So there's nothing in this sketch. Essentially it's empty, but that should be enough to program. So we compile it, and now we upload it to the microchip. And so now nothing will happen, and we have done down here, done uploading, so no errors happen, so everything is working totally fine. We can move on to making our own code.